Hello, my dear, and let's start our lecture number 12 on avionics engineering. Okay, so today's lecture named we will be containing study navigation. And the first question today's lecture is called aided IN systems and Kalman systems. You know, the time-dependent error grows of an inertial navigation system, IN, makes it necessary that some form of aided navigation system using an alternative navigation source is introduced to correct the INS error built up on long-distance flights. For example, as mentioned in previous lectures, a good quality unaided INS of only one nautical miles per hour accuracy could have a positional error of 5 nautical miles after 5-hour flight. So, a variety of navigational aids can be used for this purpose. For example, today very widely used GPS. Consider, firstly, a simple position reset at each position fixed as shown in this slide. The error growth is limited, but follows a sawtooth pattern. Look at the bottom part here. The amplitude, depending on the period between update and the magnitude of the velocity and tilt error. Now, suppose the errors present in the INS, such as attitude error, velocities error, or gyro drift, or accelerometers error, etc., and could be determined from the positional fixed information. This is what a Kalman filter does, and correction can then be applied to the INS as shown in the block diagram in the left part of the slide. The Kalman filter provides an optimum estimate of the IN system errors, considering the error present in the position fixing system. In this case, the resulting error propagation using a Kalman filter to estimate and correct the INS error follows the pattern shown in the right part, a substantial improvement. An accurate velocity reference system, such as a Doppler radar velocity sensor, can also be used in conjunction with a Kalman filter to estimate and correct the INS error. You know, in fact, a number of navigational aids can be combined with an INS in the optimal manner by means of Kalman filter. The dissimilar nature of the error characteristics of an INS and the various position and velocity to aids is exploited by the Kalman filter to achieve an overall accuracy and performance which is better than the individual system. I hope you agree with this. Okay? So, the optimum blending of the individual system characteristics which can be achieved can be seen from the brief summary of the various navigation sources as will be mentioned below. The complementary filtering of dissimilar systems using simple fixed gain mixing has already been discussed in our last lecture. I hope you remember that. Well, okay. And also in the preceding section on power and inertial mix. To recap, the various navigation sources comprises positioning data, velocity data, and altitude data. Let's divide it more precisely. Positioning data conclude GPS, VOR, DME, TACOM, terrain reference navigation system, radar, visual fixes like use of helmet-mounted sight, astro or stellar navigation, which uses automatic star tracker. Velocity data contains only two components, Doppler radar and GPS. Altitude data contains the same two components, barometric altitude from the air data computer and radio altimeter. These sources provide good information on the average at low frequency, but are subject to high frequency noise due to causes such as instrument noise, atmospheric effect, antenna oscillation, unlevel ground effect, and many others. In contrast, IM systems provide good high frequency information content about the Schuller frequency, despite vehicle motion. The low frequency information, however, is poor due to the inherent long-term drift characteristic. As already explained, it should be stressed at this point that a Kalman filter can be used to provide an optimum estimate of the error in any measuring system, and its use is not confined to navigation systems. Also, it has been particularly effective in this field. So, examples of other applications include three components: radar and infrared automatic tracking system, fault detection, and in monitoring of multiple or redundant sensors. And third, initial alignment and gyro compassing of an INS. The Kalman filter was first introduced in 1960 by Dr. Richard Kalman, and it is essentially an optimal recursive data processing algorithm which processes sensor measurements to estimate the quantities of interest or state of the system using, first of all, a knowledge of the system and the measurement device dynamics. Second, a statistical model of the system, model uncertainties, noises, and measurement errors. And third, initial condition information. The recursive nature of the filter that is using the same equation repeatedly make it ideally suited to a digital computer. The filter only requires the last value of the state of the system it be stored, and as very positive, does not need the value of the old observations to be retained. This considerably reduces the amount of computer storage required. The basic application of a Kalman filter to a mixed navigation system is shown in the flow diagram in this slide. The filter contains an error model for the system involved, enabling the dynamic behavior of the system error to be modeled. The computer contains a current estimate for each term in the error model, and this estimate, which is based on all previous measurements, is periodically updated. At the time of each new measurement, the difference in the output of the systems is predicted based on the current estimate of the errors in the system. This difference between the predicted and actual measurement is then used to update each of the estimates of the error through a set of weighting coefficients. That is the Kalman scale. The weighting coefficients are variables which are computed periodically in the system computer and are based on the assumed statistical error model for the error. The configuration takes into account the past history of the system, including the effect of previously applied information and of vehicle motions, which affect the system error. A fundamental feature of the Kalman filter is that the error measurement made of one quantity or often set of similar quantities and can be used to improve the estimate of the other error quantities in the system. For example, the Kalman filtering technique generates an improvement in the INS velocity accuracy by virtue of the strong correlation between position error or measured quantity and velocity error, which is essentially the direct integral of the position error. An introductory overview of Kalman filtering is set out in the following pages with the aim of explaining some of the essential processes and the terms used so that the interested reader or some students who want can follow up the extensive literature of the subject you may find in my recommendation on the book. Perfect. Okay. An essential element in the Kalman filter is the system error model, which models the dynamic behavior of the system error. The system dynamic behavior can be represented by n linear differential equation, where n is the number of state variables in the system. In matrix form, this becomes as the first equation on the top in left corner of this slide. X dot equals AX plus B. So here, the X is the system state vector comprising namely n state variables. Coefficient A is the coefficient of Planck matrix. B is the driving matrix, and U is the input state vector. So I want to stress here in this slide and later, both letters will be denoted matrix. Okay? So in deriving the Kalman filter, U is assumed to be a vector of unbiased white or Gaussian noise sequence. The state equations for the error in one axis of an IN system are derived below as an example. Referring to the simplifying block diagram, I just for a second show you for the previous. Yes, the position error here is a delta P. The velocity error is delta V. And the tilt error is delta theta, delta theta, okay? So we have the position error, delta P, the velocity error, delta V, and the tilt error is delta theta. The gyro drift error is W, and the accelerometer bias error is V. So the relationship between these variables are set out as a net, as these three expressions we mixing. Delta V dot, it's a delta V, yes? Delta V dot minus G delta theta plus V, and delta theta dot delta V over R plus W for drift error. Okay? So these equations can be represented, all three equations can be represented more compactly in matrix form in this part of the center of the slide. So we have three equations here on the initial data and next three matrix on the right. Or in a vector form, I doubled this one and another time, as you already saw. Okay, sorry for this. But as already explained in previous lecture, the state transition matrix Fn relates the system state vector at time t. That is, we have the xn to the system state vector at the next time n plus 1 times t. So that is, we have x divided xn plus 1, where t is the iteration period. So the relationship will be is the next expression as this formula. X sub n plus 1 proportion of Fn times Xn. Assuming a linear system, in this case, Fn, it's a exponent in power at. We may be described as a expression 1 plus at squared over 2 plus at cubed over 3 and so on. Okay? And if the iteration period t is short, we may be approximately right that Fn it's using only main component, main three components. 1 plus at plus a squared t squared over 2. For the above simple method, we may rewrite this expression as you can see on the bottom in vector 4. Namely, these four, all computed on the aircraft and maybe aerospace aircraft, using calculation by means of next 4 in vector 4, because it's very quickly and precise. So Fn, we may be represent in next expression in vector 4. And hence, delta B from n plus 1 will be expression, and the not very awful formula. Delta Pn plus T delta Vn and minus Gt squared over 2 times delta theta n. And hence, we may found next expression like. From initial estimate of the uncertainties in delta P, delta V, delta theta at fixed time t equals 0, the values at time next at time n plus 1 times t can thus be derived by a step-by-step integration process using the transition matrix at each iteration. As stated earlier, this is a simplified example to illustrate the process of deriving a dynamic error model. A typical Kalman filter INF error model consists of average 17 or 22 error states. The 19th state model comprises the following error states: 2 horizontal position error, 2 horizontal velocity error, 3 attitude errors, 3 gyro bases, 3 gyro scale factor error, 3 accelerometer bias error, and 3 accelerometer scale factor error. I hope you understand me why we use 3 in all three directions on the position. Okay? The vertical channel is not modeled till it is unstable, as was shown earlier, because of the gravity compensation with altitude, and which result in the positive feedback of altitude error. The barometric altitude information from the air data system is combined with the INS vertical channel, as shown in previous lectures, in a baro or inertial mixing loop. The GPS received error model typically comprises 12 states. The measurement matrix H capital is used to select the part of the component of the state vector X, which is being measured. So, for example, if suppose we have this total state vector X, represented by 4 components delta P, delta V, delta theta, and delta P2, all these components are the inertial system errors, and we have a new expression, delta P2. This is the error in the position reference system. To extract delta P minus delta P2, the measurement matrix H will be represented as this expression on the top right corner of this slide. The covariance matrix of the estimation error is formed by multiplying the error state vector matrix by its transpose. If we have the transpose one side, X transpose, the transpose of a matrix means interchanging the rows and columns of the matrix. Okay? So, for example, if we have a matrix M represented as coefficients A, B, C, D, okay, components, the transpose of matrix M transpose will be AB instead of row, will be a column, and CD instead of row became a column. Okay? So, as a simple example, the covariance matrix P of a state vector X comprising position, velocity, and tilt vector. Position, velocity, and tilt vector, term, and that is we may represent in this expression. And thus, the P in vector form will be equal X times X transpose. And P in matrix form will be represented as this expression, vector expression, on the bottom right corner of the slide. Okay? So we may represent the P vector in the final expression as this one on the top left corner of this slide. It should be noted that the covariance matrix is symmetrical about a diagonal, with the diagonal element comprising the mean square position, velocity, mean square position, velocity, and tilt error respectively. The off-diagonal term a cross correlation between these same three quantities. The covariance matrix changes with the time as the initial errors propagate with time. It is modified with time by means of the transition matrix using the following relationship, as you can see here in the middle. Pn plus 1 submitted equals Fn plus Pn times times Pn times Fn in power t. In power t, F means it's transposed from Fn. Okay, so the use of the Kalman filter equation is briefly set out now. The purpose of the Kalman filter is to provide an optimum estimate of the system state error and interaction of M. And this is denoted by X and cat using this cat. The circumflex indicate a best estimate. The filter may be described, in this case, in two stages. Extrapolation indicates the period during which the filter simulates an action of the system between measurements. Update occurs when a measurement is made on the system and is incorporated into the filter estimate. Quantities after extrapolation immediately preceding the nth update are shown in the manner here x and hat as a minus, and those immediately succeeding that update as x and hat plus. Okay, during extrapolation, the filter estimate of the system state vector is modified according to the best available knowledge of the system dynamics, as you can see here in this bottom expression. Fn minus 1 in previous step times x hat in previous step, but future plus. Okay? And the error covariance matrix is also extrapolated in the right side on the top. Pn minus proportions Phi in previous step, Pn from previous step for future, and times F in previous step transpose, and plus Q. Q is the covariance matrix of the random system disturbance. During the filter update procedure, the difference between the actual measurement and the measurement made of the estimated state is weighted and used to modify the estimate state, as you can see in this second expression. X hat n in the future. Yes. So this estimation state, it will be x n hat from minus plus kn, and another expression in parentheses, zn minus hn, xn hat from. Here we have another new component, zn. This is an actual measurement which made of the state variation. And Kn, if this is a Kalman gain matrix. So, in this case, the weighting factor or Kalman gain are calculated from the current estimate of the error covariance in this expression, Kn. Here we have Pn as minus time h transpose time expression in parentheses. H times Pn is minus times n h transpose, and plus R. I hope you remember. R is a measurement noise covariance matrix. Okay? In this case, the error covariance matrix is then will be also updated in this expression and equal P prime and this very simple. Okay? Are you agree? Any questions or propositions? For some people so interested in this, you might be asking me in questions after the video. I may be speaking with you directly, or you have in every lecture, you may find my email. So any questions you're interested in or making some proposition, you may ask me for that. Okay? Let's go. Next question, today's lecture, attitude heating reference system. As explained in the introduction to this lecture, modern attitude heating reference systems are stripped-down systems, excluding solid-state gyros and accelerometers, and are basically like modern stripped-down IN systems, inertial navigation systems. The major difference are in the accuracy of the inertial sensor and their consequent cost. There is no significant difference in reliability between of the two systems, as both explore solid-state exploitation. Solid-state implementation. The key features of Schule tuning using very high accuracy gyros and accelerometer is very high and is certainly essential for vertical reference accuracy the system, which provides around 0.3 minus of R for a good quality INS. And this accuracy is not dependent on the aircraft acceleration profile. A fundamental characteristic of Schule tuning. The lower limit of in terms of gyro and accelerometer accuracies for Schule tuning to be effective in providing an acceptable vertical reference accuracy in an AHRF system is around 0.3 degrees per hour. The gyro drift rate, its uncertainty, and 500 milli micro G. It means exactly 2 minutes of arc tilt. For accelerometer bias uncertainty, such sensor error would produce vertical error of 4.2 minutes of arc and 2 minutes of arc respectively, and the resulting standalone vertical accuracy, which would be around 0.1 degree. An alternative method of monitoring the vertical reference, which enables a lower performance and hence a lower cost gyros and accelerometer to be used in an AHRS, is based on the use of an independent velocity source. This is a technique is known as Doppler or inertial or air data or inertial mixing, depending on the source of the aircraft velocity. The errors in the vertical reference resulting from the effect of the acceleration during maneuvers and can be kept small with such a monitoring system, given an accurate velocity source. Small transient errors can be induced in the vertical reference due to changes in gyro drift rate or accelerometer bias error. The gyros and accelerometer should thus be of reasonable accuracy. Also, they can be up to 2 orders of magnitude below inertial standard. The method uses the same techniques as used in inertial navigation systems to derive the aircraft velocity components from the AHRS accelerometer, by integrating the suitably corrected accelerometer output with respect to the time from known initial condition. The major source of error in the initially derived velocity component arises from the vertical error or tilt error in the AHRS, producing gravitational acceleration errors which are integrated with time. The inertially derived velocity components are therefore compared with the velocity components measured by the reference velocity system. The velocity differences are then fed back to correct the vertical error in the attitude reference and the inertial velocity error. And this figure on this slide illustrates the basic concept. In the case of a Doppler velocity sensor, the Doppler and inertially derived velocity are compared along local NED axis, as the Doppler is a key part of the navigation system. Okay? In the case of lower accuracy AHRS system, the comparison of the air data and inertial velocity component is generally made along the aircraft body axis. It's a logical. The mechanization of an air data or inertial velocity mixing system to monitor the vertical reference of a strap down AHRS is described as its 3 main components. A, the use of air data derived velocity as opposed to Doppler. B, the use of aircraft body axis as a reference frame of axis. And C, the application to a lower accuracy AHRS with lower cost gyros in the few degrees per hour bias uncertainty performance bracket. So, derivation of velocity component from the air data system. The air data system provides outputs of true airspeed, which we mixing here, submitting here as the V sub T. And the angle of attack or incidence alpha. And the side slip incidence angle beta. Okay? So the air data derived forward velocity, we denote it here as the U sub A. This is a side slip velocity. V sub A and vertical velocity, and WA computed from the air data system output with it, alpha and beta, and the suffix A been used hence to denote it the source of U, V, W, in our case as U as UA, V as UV, VA, sorry, and W as WA. In this case, inertial derivation of forward velocity and side slip velocity will be represented as these three expressions. Maybe some slight changes in this my figure. I'm telling you, for EX proportional U dot minus V sub R plus WQ, just like all about 2 you can see in this slide as well, right? So referring to this figure on the left, it can be seen that the gravitational acceleration component, which component? G X, G Y, and G Z, respectively may be expressed as you can see in this simple equation, okay? So the outputs of the forward, side slip, and vertical accelerometer are denoted by as A sub X, A sub Y, and A sub Z, respectively, and represented as this expression. So the accelerometer bias error are ignored at this stage of simplicity. So from all these equations, it can be seen then the U dot and V dot can be obtained by computing the centrifugal acceleration component term. Centrifugal component term is minus VR plus WQ, centrifugal component. This has another direction, okay? And we have another direction, UR minus W. And the gravitational acceleration component term, G sub X, G sub Y. And the subtractive this computed component from the accelerometer output in X, A sub X, and A sub Y, respectively. The inertially derived velocity components U sub I and sub 1 and V sub 1 are then obtained by integrating of U, so Y we have for 1 U dot and V dot respectively with respect to the time, okay? So the air data inertial velocity mixing loop. I should say that overall air data or inertial velocity mixing loop are shown in this slide. The computed centrifugal acceleration component term, namely minus VR plus W, I hope to show you, minus VR plus W, yes, and UR minus WP are derived from the air data velocity component as U, A, V, A, and WA, and so are computed with respect to wind axis. The fact that the air mass is used as the reference frame and the wind axis are moving does not affect the values of these computed centrifugal acceleration terms, which provided the wind velocity as a constant. Any acceleration of the reference frame due to changes in the wind velocity, however, can introduce error. The assumption is made that the air mass acceleration generally appear as gusts of comparative short duration, which can be effectively smoothed by the air data or inertial mixing. The gravitational acceleration component, which we represent as a G sub x and g sub y are computed from the values of the pitch angle theta. Okay, pitch angle theta. Yes, we have. And we have correct for g sub x sub y. Certainly, as you can see, from altitude integration block, we have the influence of bend angle F capital, derived from the altitude computation using the incremental angular theta from the step down gyro. Okay, so integrating the values of u dot and v dot with respect to time yield us, as you can see, u1 of the integration blocks, yes, u1 and v1, u1 and v1 gets into the summation, yes, multiplication. And these values are subtracted from the air data derived values as a UA and VA to yield us UA minus U1 and the same VA minus V1. The Coriolis acceleration components have been ignored here for simplicity, because the air mass, of course, rotates with the Earth. The major errors in deriving U1 and V1 are due to the tilt errors. Tilt errors we have as a delta theta and delta F. Delta theta and delta F is deriving the pitch angle of theta and bend angle F capital from the gyro out, assuming the errors in the computed centrifugal acceleration as a small. The accelerometer bias errors are also assumed to be small. Okay, so in this case, these tilt errors, delta theta and delta F, result in acceleration errors. Acceleration errors will be g times delta theta and g times delta F, assuming that delta theta and delta F, as I just mentioned, are small angles. Okay, in the computation of g sub x and g sub y, which are integrated with time, causing a difference between u1 and ua, and the same identically uv1 and va, unless corrected. The air data for inertial velocity error, ua minus 1 and va minus v1, are thus fed back as shown in this expression, in this figure. So to the u1 plus to the u1 and v1 integrators to slave u1 and to ua, and slave v1 to va. Yes, so we have in this of the computed va, is that v1 to va and u1 to ua, and the next to the attribute computer to correct the pitch and bend angle, tilt errors, and reduce these zeros. In this case, proportional plus integral control will be expressed as a two, this expression chi2 from velocity error plus k3 and integral from delta t. This is used in a feedback, yes, in a feedback to the altitude computer, yes, okay, to eliminate steady state chill error due to the gyro bias. The values of feedback gain, as we can express as a K1, K2, and K3, are selected to ensure good damping of the closed loop and good overall accuracy. These loops are also used to align the AHRF when the aircraft is stationary on the ground. In our case, SUA and DA are both must be equal to 0. Okay? So, I want to say that any velocity errors result from initial tilt error, and so are fed back to correct the vertical reference. But it should be noted that the aircraft is usually fairly level when on the ground, so that the pitch and bank angles are generally small. The coarse values of pitch and bank angles used to initialize the attitude computation from the gyro incremental outputs and can thus be set at 0 and subsequently corrected by the alignment process using the accelerometer output. The gyro-derived attitude information is coupled in through a high-pass filter with pass frequencies of the order of 0.003 Hz. This is a period of 5.6 minutes approximately. Overall, so that the short-term measurements of the attitude changes of the aircraft and is provided mainly by the gyros. The attitude reference derived from the accelerometers is filtered by a low pass filter, which smooths the noise present and attenuates short period fluctuations, but retains the long-term accuracy of the gravitational reference. But I should denote it you another time. It should be noted that there are considerable variations in the implementation and sophistication of the mixing system used by strap-down AHRS manufacturers. All this description is a simplified outline only of the basic principle used. The correction for Earth rate and vehicle rate have also been omitted for clarity. Okay? So, in the event of the loss of air data velocity, the AHRF reverts to a gravity monitoring system, basically similar in principle to that of a simple standby vertical gyro unit, VGU, vertical gyro unit. The computing power available, however, within the embedded processor in the solid state AHRF enables a more sophisticated leveling, or as sometimes calling erection loop, with variable time constant to be implemented. The erection cutout strategy during maneuvers can also be made more adaptive. Okay? 1 second. Oh. Let's describe azimuth monitoring using a magnetic heating reference. Now, gyro compassing is not suitable for an AHRS with lower accuracy gyros, because alignment errors of 1 degree would result from using gyros with 0.1 degree per hour bias uncertainty. And typical AHRS gyros are in the 0.3 degrees per hour and maybe up to 5 degrees per hour bias uncertainty bracket. And so that other method must be used for initial alignment and subsequent monitoring of the aircraft heading. The heading can be unmonitored for several hours if the gyro drift is less than 0.01 degree per hour. So, magnetic monitoring using the Earth's magnetic field as the classical in the previous time as the directional reference is generally used for the alignment and monitoring of the heading output of an AHRF using gyros which are not of inertial quality. So why, until in modern all of this avionics, we may find, as in passengers, as in private, as in military aircraft, classical magnetic compass. So this is a self-contained and simple system of relatively low cost and enough high reliability. Using modern magnetic sensor with computer compensation of the sensor error, together with an accurate vertical reference from the AHRS enable the heading errors to be constrained, generally to less than 0.7 degrees for latitudes up to about 60 degrees. No, more higher, we have explained as we have before the polar and south polar region effect. A magnetic heading reference is also used for coarse initial alignment of an INF with the fine alignment carried out by gyro compassing. And it should be noted that the Earth's magnetic poles are offset from the Earth's polar axis, so that the direction of magnetic north differs from the direction of the true north. The differs from the true north geographic. And the difference between the two is known as the magnetic variation. This is not constant and varies over the Earth's surface. Concentrations of iron ore in the Earth's crust, for instance, can cause significant changes or magnetic anomaly. I remember from my previous career as a pilot, as a Ural anomaly, as a magnetic in this region compass, it became absolutely right. So, in this case, we may say as a significant changes, concentration iron, or magnetic anomaly. It's usually maybe in the local magnetic variation. There are also long-term changes in the magnetic variation over several years. Magnetic variation has been accurately measured over large areas of the Earth's surface, so that the magnetic heading can be corrected to give true heading by adding or subtracting the local magnetic variation, which can be stored within the system computer. Today, no need calculated as before with rulers or special devices. So the presence of magnetic material on the aircraft causes local distortion in the Earth's magnetic field, measured within the aircraft, introducing a further error called magnetic deviation. This is defined as the difference between the direction of magnetic north measured in the aircraft and the same location in the absence of the aircraft. Extensive measurements are made with the aircraft on the ground to establish the magnitude of the error due to the aircraft's inertial magnetic environment. The Earth's magnetic field is inclined to the angle to the horizontal in general. This angle is known as an angle of dip and is dependent on the latitude, and being roughly 0 degrees near the equator and up to 90 degrees at the north or south magnetic pole. The magnetic heating is determined by measuring the direction of the horizontal component of the Earth's magnetic field. Error in measuring the orientation of the magnetic sensor with respect to the vertical will result in a component of the vertical magnetic field and be measured, and will hence introduce an error in the magnetic heating. The vertical magnetic field component is equal to the horizontal magnetic field component multiplied by the tangent of the angle of dip. And at a high latitude, the vertical component can be several times greater than the horizontal component. Yeah, that's very specific. By magnetic heating, error caused by a vertical error is thus geared up by the tangent of the angle of dip. For example, an angle of dip of 68, if you suppose you're flying in North America, results in a magnetic heating error which is 2.5 times the vertical error. The importance of an accurate vertical reference can thus be seen. But it should be noted that the magnetic heating reference becomes unstable at very high latitude as the angle of dip approaches 90 degrees. And the horizontal component of the magnetic field approaches 0. The unmonitored gyro heating out must be relied upon the flight sector over the polar region. This is very, very specific flight. And the magnetic heating is measured by an instrument known as a 3-axis plug gauge director in conjunction with an AHRS, which provides the vertical reference for the plug gauge detector. That system comprises 3 magnetic field sensors of plug gauge, which are mounted orthogonally perpendicular to each other in a block directly fixed on the airframe. So in this case, we call strap down with the sensor axis parallel to the principal axis of the aircraft. The location of the plug gauge triad for all 3 axes, right, is chosen to be as far away as practical from magnetic field sources, AC and DC, within the aircraft. Possible locations may be in one of the wings or in the fin. The small size and electrical output of the plug gauge giving a high degree of flexibility in the installation. The typical plug gauge detector consists of primary and secondary coils bound on a pair of soft iron. The primary is excited by the audio frequency sinusoidal current of the sufficient amplitude to drive the course into saturation at the current peak. The secondary, which is wound differentially about the two chords, picks up the second harmonic content caused by the change in inductance saturation. And this output is approximately proportional to the magnetic field strength for applied static fields, less than the saturation field of chords. To improve the linearity of the output, the floodgates are operated in a feedback mode. The output of the secondary is demodulated and feedback to the primary. So the net field in the core is zero. And the DC current in the primary is then a measure of the impressed magnetic field. The floodgate, however, also measures any low frequency magnetic field, and not just component of the Earth's magnetic field, along the measuring axis of the floodgate. The floodgate output are thus in error from what is known as hot iron. Hot iron effect due to the unwanted AC magnetic field, and from soft iron effect that distort the Earth's magnetic field through the magnetic material in the aircraft. The components of the Earth's magnetic field with respect to the aircraft principal axis are denoted as H sub X, yes, H sub Y, and H sub Z along the forward, side slip, and vertical axis respectively. Okay? These true components, also H sub X, H sub Y, and H sub Z of the Earth's magnetic field along each axis can be expressed in terms of a set of equations which relate the total measurement xm, ym, and zm. So we have three expressions here on this right corner, right? This is to account for this misalignment, and the hot iron and certainly the soft iron effect, which are characteristic of the floodgate and their environment in the aircraft. So this set of equations in this form, as I just mentioned, and here we have the coefficients A1, A2, A3, and certainly B1, B2, B3, and finally C1, C3, C3, and finally D1, D2, D3 are measured and stored in the AHRS computer, so that the floodgate measurement can be corrected and the true components HX, HY, and HZ of the Earth's magnetic field can be determined. Referring to this figure, there is no component of the Earth's magnetic field in the horizontal plane along the heating axis, namely H1, and the right angle to the heating axis, H2, are given by these two expressions. Generally, it's not complicated expression, right? The horizontal component of the Earth's magnetic field, H sub H here, is therefore equal as a square root from these two mentioned figures. h1 squared plus h2 squared, square root from these two components. Yeah, two components as a heating axis and the both heating axes. The aircraft's magnetic heating psi sub n, it will be cosine, yeah, 1 over cosine angle, h1 over h sub h, or simply 1 over sine h2 over h sub h. The computational process in deriving the magnetic heating M are shown in this figure. And this comprises three main components. First, computations the true components h sub x, h sub y, and h sub z of the Earth's magnetic field with respect to aircraft axis, right? From the measured output of the three plug gates. Plug gates, we have xm, ym, and zm. Okay? And the store coefficients we just mentioned, a1, a2, a3, b1, from b1 to b3, from c1 to c3, and from d1 to d3, as in previous equation of the previous one. Second component, computation of the horizontal component of the Earth's magnetic field along the heating axis. In our case, here is the H1 and the right angles of the heating axis H2 using equations as we already showed. And third, computation of the magnetic heating angles C sub M from these two expressions on the bottom. Psi M, yes, and this one. The gyromagnetic heating monitoring system is illustrated in this slide. A basic second-order mixing system been shown for simplicity. More complex mixing system using a Kalman filter can be employed too. And referring to this expression, we may say that psi G, not CF, psi G, yeah? Or look at this one. We have heating axis and magnetic to the north. The angle, magnetic heating psi M, yes? And we have the heating magnetic angle as a psi G angle, yeah? And it will be gyro derived heating from the step down. And this case, it will be heating as the psi G, the psi, which is the true heating angle, and plus integral from W is a gyro drift rate times dt. We may say that exists another psi when J over M, if this is a gyro or magnetic heating. And in this case, we may use another coefficient. Look at this one. I just said JR sub M, J, CJ, gyro derived heating from the step down system. And in this case, J sub G, gyro derived heating, will be expressed as the psi true heating angle plus integral W times dt. W is a gyro drift rate. Next expression we're using as this psi J over M is a gyro or magnetic heating. And we have two coefficients, K1 and K2. K1 is a mixing gain for psi M minus psi j over m feedback. And K2, the mixing gain feedback between psi m and minus this double dt. Double dt known is this. Only one time. This minus my fault. Okay, this is extra. It's known. So from the block diagram, it can be seen that our psi gm expression will be two integrals as we have here. Why I'm writing here in this case? Japanese secondary set. Because I'm using double integration. Integration one time, and the same. So in this case, when we have a complex integral, double integral, every time. In our case, we two times integrated in time, but we can integrate it in another value, like direction. So we maybe both direction or more. Okay. So why we use it two times dt here? Differentiation equation twice. We need to substitute psi dot psi dot for psi sub g. That give us this bottom expression on the top bottom. Okay. And the dynamic response of the system is that of a simple second order system with an undamped natural frequency. Undamped natural frequency is omega naught. Omega naught equal square root from K2. And another damping ratio, it's a J here. It's equal K1 divided by 2 square root from K2. The integral feedback gain, in our case, K2, determines the undamped natural frequency. And the proportional feedback gain, K1, determines the damping. So K1 and K2 are determined by the value of the gyro bias uncertainty. And the need to have a well-damped closed loop response of J equal or near to B1. From this equation, we can write our first expression that have long expression near the half slide, but means three components. Yes, 1, 2, 3 components. Ignoring the gyro bias uncertainty term, double, as it has zero contribution to psi in J sub M, if W is constant. And so this we may rewrite our expression more compact for psi j or m, f1 from d times psi m plus f2 from d times psi. So what it means f function? F function, we have our expression f1 and next expression f2 from d. For simplicity, we got this. So the magnetic heating psi m component psi g over m is coupled through a low pass filter of transfer function, in our case f1 from d, and this greatly attenuates the magnetic noise content of psi m output. And short-term transient error such as would be caused by flexure of the structure at the flex gate sensor location under the maneuver law. The gyro measured component psi j from m is coupled through a high path, or washout filter of transfer function F2 from D. And this enables the changes in the heating to be measured without lag, but ensures that the steady gyro bias W, is DC block, or as sometimes called, for washout. The complementary filtering thus enables the best of both worlds to be achieved. The basic accuracy and repeatability of the magnetic heating sensor is retained, but any noise and transient error during maneuvers are heavily smoothed and filtered. The excellent dynamic response of the gyro system is retained, and the gyro bias is DC block. There are also no steady state magnetic heating error due to the gyro bias. And figures on this slide, it's very simple, illustrate the system response to a constant rate term, assuming a near critically damped system. In next lecture, we will be studying GPS, or global positioning system. For this moment, I think it's enough, right? I hope you enjoyed our lecture. And as usually, I'm looking forward to seeing you next time. Bye.